Okay, I've managed to scramble some previous questions whereby I just want us to go through so that we can summarize chapter 2 and chapter 3 according to what we have already done. Remember, I told you that we will only have or we'll only continue with our theory class after we are done writing test 2, of which you are writing on Saturday. So I fail to understand when you send the message on the group, are we attending, are we attending? It shows that those are the people that doesn't even come to class. Because if you come to class, you will know what I said in class and stop asking questions that honestly they are not relevant to what we spoke about. Because sometimes it becomes so annoying. But well, okay, let's continue. I hope all of you can see the screen. I share the screen and also I share the question paper. I share the practice questions. I asked Anle to send them to us. She can email them to you via Vutela. You'll get them on Vutela, and also you can go through them yourself so that you can practice and prepare yourself for the test of Saturday. Okay, to begin, we'll start with revision of chapter 2, whereby you know that in chapter 2 we were dealing with rectifiers, and I told you that the most common rectifier that we are going to work with, it is your bridge rectifier. It is your bridge rectifier. So I want us to go through the bridge rectifier so that we can check exactly what is it that we can expect in terms of the bridge rectifier. Now, if I can start there, which is your question 1, or which is number 1, it says a circuit diagram of power supply is shown in figure 3. This is your figure 3. This is your circuit. Then it says the diode D1 to D4 are germanium diode, which means D1, D2, D3, and D4, they are germanium diodes. Now, remember, for practical purpose, you will see that we don't use the germanium, but we use the silicon. But because this is the theoretical analysis, remember I told you with the diodes, we have got 2 types of diodes, which is your silicon diode and also your germanium diode, which means here we are using the germanium diode. And we know that if we use the germanium diode, with germanium diode, we will have a barrier potential of what? With the germanium diode, we will have a barrier potential of what?
0.3.
Yeah, 0.3 volts. That is your germanium diode. That is your germanium diode. Then therefore, from there, then we know that if we work with these already 0.3, it is measured across each of these diodes that you see here. Then it says all calculations must be shown. Sorry, let me just take this quickly. I've got class. I'm in class now. I'm in class now. Can I call you after class? So that is your germanium diode. Therefore, now we'll go and say the first question. It says you must calculate the secondary peak voltage. Now, with the secondary peak voltage, which means you're given a transformer, you will see that on this transformer here, you have the primary side, and then here you will have the secondary side, which means what they're looking for, it is the voltage which is measured from here up to here. This is your secondary side, which means now if we want to get the secondary side, we go and check. In the primary side, what are we given? Remember, we have got an equation, and that equation, it says V of primary over V of secondary is equals to N of primary divided by N of secondary. That is your equation. So with this equation, which means now we must go and say what we are looking for. We are looking for V of secondary. And for us to find V of secondary, you will see that you are going to say V of secondary is equals to, now we need to manipulate this formula here. When we manipulate this formula, you will see that the N, it is your turns ratio. Already, you are given your turns ratio. That is your turns ratio, which is 1, so which is 5:1. Therefore, if it is 5:1, which means you're going to say 1 divided by 5 multiplied by then your secondary, sorry, your primary voltage, which is 130 volts. Now, this 130 volts, remember, it is what? It is your RMS. Always you must remember that is your RMS. Therefore, what will be your V of secondary? But now, with this V of secondary, first you're going to get it as a RMS. Then from there, we will have to convert it to peak. And we know that when we convert from peak to RMS, so when we convert from RMS to peak, we must go and multiply by √2. In this case, what would be your V of secondary?
26 volts RMS.
26 volts, which means it is going to be 26 volts RMS. That is your RMS voltage. Therefore, for you to get the peak voltage, what are you going to do? You are going to multiply the RMS voltage by what? By √2. You're going to multiply your RMS voltage by √2, which will give you what?
36,770.
36,770.
Yes.
Volts, which means that is your peak voltage. That is your peak voltage, which means now you have calculated the secondary peak voltage. Are we together? You still all remember this?
Yes, sir.
Okay, good. Then from there, then it says you must calculate the peak rectifier voltage. You must calculate the peak rectifier voltage. Remember, from the transformer, you have got the primary side, then you have got the secondary side. You take the secondary side, you convert it into peak, then that signal goes through your diodes up until you measure that voltage here. You measure that voltage here, which means the voltage that you see here, it has been rectified by these diodes here. Your voltage that you find, it has been rectified by these diodes here. Therefore, which simply means that if you want to find your secondary voltage, wait, let me just go down. If you want to find your rectifier voltage, therefore, you're going to say your V peak, but the rectifier voltage. It simply means that the voltage that went through the diodes. Remember, your diodes is the one that gives you the rectifier. Therefore, it is going to be what? Now, remember, when I explain this, I said to you that you will see that the signal, it is going to pass through two diodes so that it can get to the negative side. It needs to pass through two diodes. Therefore, your V secondary, your V peak rectifier will be your V peak, but the secondary one. Your V peak, but the secondary one minus double your V of the diode. In this case, what is V of the diode? You will see that that is 0.3 volts. Are we together? Therefore, now you're going to say, what is V peak of secondary? You determine V peak of secondary, which is 36,770 minus 0.6, which gives you what?
36,170.
36,170 volts, which means that is your V peak rectifier. Are we together? Up to so far, are we together?
Yes, sir.
Yes.
Yes, sir.
Okay, good. Then from there, then we move to the next question. The next question says, from the figure 3, which one is figure 3? This is figure 3. From figure 3, then it says, if R load is given by, you are given R load, you can see R load here. This is your R load. If R load is given by 3.7 kilo ohm, and your capacitor is given by, this is your capacitor, it's given by 1000 microfarad, which means you have got given information. Then it says you must calculate the ripple factor and draw a fully labeled output waveform measured across your load, which means now I need to go and determine the following, which is your ripple factor. What is your ripple factor? You will see that when you determine the ripple factor, you're going to say my ripple factor is given by your V ripple peak to peak divide by your VDC. You still remember the equation for the ripple factor. Therefore, now I need to find what is my V ripple peak to peak, and also I need to find what is my VDC. So which means, therefore, now I can go and say, first, let me start with my ripple. So my V ripple peak to peak. Let me start with my V ripple peak to peak. How do I determine V ripple peak to peak? You will see that for you to determine V ripple peak to peak, you're going to say 1 divided by 2 times the frequency times the capacitance times your load resistor. All of these multiplied by V peak but of the rectifier. Don't make that mistake. It must be V peak of the rectifier. It simply means that if I went back to my the voltage which you find here, which is your rectifier voltage here, that is where you're going to find your V peak rectifier, which means with this V peak rectifier, it is the one which is supplying the voltage to the capacitor and also the voltage to your load resistor. Therefore, now I will go and say, which means according to this, if I substitute, what am I substituting? You will see that I'm going to substitute and say 1 divided by 2 times, what is your frequency? You will see that if you go back to your circuit, you will see that your frequency is what? On your circuit, your frequency is what? Your frequency is 50 hertz. Yes, which means now you're going to say, now here, I must multiply this by 50 multiplied by, what is your capacitance value? This is your capacitance value, which is your 1000 microfarad. Now, you know that 1000 microfarad is the same as multiplied by 10 to the exponent minus 6. Are we together? Multiplied by also your resistance value, which is 3,7 kilo. And we know that kilo is the same as multiplied by 10 to the exponent 3. Multiply micro, which is multiplied by 10 to the exponent minus 6. Kilo, which is multiplied by 10 to the exponent 3. Then all of these must be multiplied by your V peak rectifier. What is your V peak rectifier? You will see that your V peak rectifier, it is what? It is your 36,170, which will give you what? Work with your calculators, which will give you what?
.098.
Eh?
0.098.
What?
97,757 millivolts.
575. My
97, comma
7
5,
7
57,
5. You're 757.
90. You said 90?
97,757
Okay, 757
millivolts.
millivolts, which means that is your V peak. So V ripple peak to peak. From there, then you will go and say, now I need to go and calculate what is my VDC. Now, for you to calculate VDC, I should have left enough space, okay, but that's not a problem. Okay, let's just hope this is going to work out. Okay, now, if you want to calculate your VDC, which means now your VDC will be given by 1 minus 1 divided by 2 times 2 of the frequency, or double the frequency, multiplied by your capacitance value multiplied by your load resistor. All of these must be multiplied by your V peak rectifier. That is what? That is your VDC. When you substitute, what are you going to get when you substitute? Which means you're going to have 1 minus 1 divided by, what is your 2 times 2 multiplied by, what is your frequency? We know that our frequency is 50, multiplied by the capacitance value, which is 1000 microfarad, multiplied by your resistance, which is 3,7 kilo ohms. All of these multiplied by your V peak rectifier. What is your V peak rectifier? There you will see that it is 36,170. 36,170. Then all of these, when you punch it on the calculator, what do you get?
$36,121.
Which is
volts.
36,121
volts.
121 volts.
Yes.
Which means that is your VDC. Therefore, now you can go and determine what is your ripple factor. Ripple factor, your V peak to peak, so V ripple peak to peak divided by VDC. You know your V ripple peak to peak, which is what? Which is your 97,757 millivolts divided by your VDC, which is 36,121 volts, will give you what? What will be your ripple factor?
Zero comma 0,027.
0,027. That is your ripple factor, which means if you multiply this by 100, you'll see that you will get 0,27, 0,27, what do you call this? Not 0,27. It's going to be 0,27% if you multiply it by 100, but you can put it in percentage, or you can leave it as it is. It is still the same to me. That is your ripple factor. Once you get these, then it says, now what must you do? Now you must draw a fully labeled output waveform measured across R load. Now, if you go back, this is your R load. This is your R load, which means we need to see what will be the waveform that you measure here. What will be the waveform that you measure here? Now you will see that the waveform that you're going to measure here, this is going to be your waveform. You will see that you're going to have your axis, your y-axis, and you're going to have your x-axis. Then from there, now the voltage that you see here, or what you see with this load here, it is the... Switch off the mic. What you see here, you will see that your signal will start from the beginning. Then when it gets to the maximum, then it will create a ripple.
In the middle, I know it's cut. I cut it for you.
Guys, switch off your mic.
I don't know.
Oh, sorry.
Okay. I don't know.
Then, when I want to label this thing of mine, then I will go and say, okay, I've got this one there, which is the peak. This one, it's my ripple factor. Now, this is your ripple voltage. This one here, it is your ripple voltage because you connected the capacitor. If you didn't connect the capacitor, which means your signal was not going to be smooth, then you were going to find a pulsating DC. Because you connected the capacitor to filter the signal, now you have got, this is your filtered signal. With this filtered signal, then you will start seeing that the magnitude that you see here, from here to here, that is your V peak. So that is your V, not V peak. Sorry, let me do this. That is your V ripple peak to peak. This voltage that you see here, that is your V ripple peak to peak. Then from there, now you will see that the maximum peak that you see here, the maximum peak that you see here, that is your V peak rectifier. The maximum that you see there, that is your V peak rectifier. Then from there, then you will see that just above, so just below your peak voltage, then that is where your VDC will lie. Just below the peak voltage, that is where your VDC will lie, which means with this dotted line, that is your VDC. Remember, the reason why I'm writing, it starts from 0. The graph must be fully described. Now, you will see that your V peak to peak, you have calculated it. The reason why I wrote V peak to peak is because V ripple peak to peak is because already I've calculated down here my V peak to peak ripple. Here you will see that I've calculated the V peak to peak ripple, and also I have calculated this rectifier here. This is my rectifier here. Then my VDC, I've calculated my VDC, which means when I look at what you have done here, then I go back and check, oh, V peak rectifier, it has been calculated, which means it is indicated there. This is the same as when I see that value there. This ripple voltage, it is when I see this value here, which is this 97,757 millivolts. Then my VDC, this VDC value here, it's like I am seeing that VDC there. There is your graph that you need to do, which is your which is your 1.3 question 1.3. Any question up to so far? Anything difficult there? Anything that you don't understand?
So to say, you said, how do we convert the ripple voltage into 0,007?
You said what? What I say?
I was asking the answer for the ripple.
I said the ripple factor. The ripple factor. I know you're talking about the ripple factor. It's either you leave it in here or you write it in percentage.
So the answer that we get on a calculator, we just have to times it by 100. Because like here on my calculator, it gives me 2,706 times 10 to the negative 3.
Yeah?
The answer that I got for the ripple factor.
But that is scientific notation.
Okay.
You must write it as decimal. Can you see here? It's written as decimal.
Yeah.
So which means if you want to convert it into percentage, you must go and multiply this by 100, isn't it?
Yeah, it is.
Then it's going to give you in percentage.
Oh, okay. So thank you.
Yes. It's either you write it in percentage or you just write it as decimal. You write it in percentage, you write it in decimal, I'll give you full marks. Because remember, the factor doesn't have a unit.
All right. Okay, thanks.
Yes, no problem. Any question? Anyone? Must we move on?
Yes, sir.
Okay, good. Now, that is how you answer that one there. Then you will see that number 2. Again, we have got a circuit, which is your full bridge rectifier circuit, which is your power supply. Then it says, consider the following full bridge rectifier circuit with given parameters. You have got your N1, which is given as 12. This is your N1. Now, this N1 simply means that is your primary side. N2, which is 1, your secondary side, which means the ratio it is what? It is 12:1. Then the capacitance value is given. That is your capacitor. But the resistance value, it says it is unknown. Your R is unknown. The diode, it is silicon. Which diode? From D1 up to D4. That is your silicon. Then from there, now we'll go and say, okay, how do I work with this? How do I work with this? Now, then it says I must calculate the unknown value of the resistor. I must calculate the unknown value of the resistor. That is the resistor. If the value of VDC is given there, if the value of VDC is given as what? 12,440 volts. Can you see you are given the value of VDC? Are we together? It simply means that if VDC is given, what is missing here in the equation that I need? Sorry. Hello? I'm in class. Can I call you back? I'm in class. Can I call you back? Your value of VDC is given. It simply means that we have got 2 equations that we can use. Remember, both of the equations, they consist the value of R. Now, let's look at this. If it says VDC, it simply means that now I'm going to say, oh, I know that this equation of VDC is equals to 1 minus 1 divided by 2 times twice the frequency, the capacitance value, and the resistor. All of these multiplied by my V peak rectifier. That is the equation. Are we together? Now, you will see that on this equation that I see, oh, VDC, it is that one there, 12,440 volts. Now, 1 is a constant value. Minus 1 divided by 2 multiplied by 2, those are constant value. The frequency, frequency is given there from the circuit, which is what? 60 hertz. Then the capacitance value, the capacitance value, it is there. What is missing? You will see that your resistance value, it is the one which is missing. And also, if you look at this as the resistance value missing, multiplied by your V peak rectifier. How do I get this V peak rectifier? Oh, if I remember there, it says V primary divided by V secondary is equals to N of primary divided by N of secondary. If I look at this equation, which means here I can go and say V of secondary is equals to 1 divided by 12, which is this ratio here, multiplied by 120 volts. Are we together? Therefore, with these, what am I going to get? 120 divided by 12, what do I get?
10.
I get what? 10 volts. These volts that I'm getting, it is what? It is my RMS. Are we together? Then from there, then I can say V peak secondary is going to be what? It is going to be this voltage here multiplied by what? Multiplied by root of 2, isn't it? If I multiply this voltage by root of 2, what do I get?
14,142.
14,142.
14,142, which means that is the voltage that I get. Then from there, V peak rectifier. V peak rectifier will be given by V peak secondary minus 2 times your VD. In this case, what is your VD? Your VD in this case, it says what? It must be silicon, isn't it? If it's silicon, it simply means the voltage is what? 0,7 volts, isn't it? Which means if it's 0,7 volts, which means here it is going to be 14,142 minus 1,4 volts. Because if you double this one, you're going to get this, which will give you what?
12,742 volts.
Eh?
12,742 volt.
Which means it will give you 12,742 volts. Are we together? Which is your V peak rectifier. Now I know what is V peak rectifier. I know what is, which means here I know what is VDC. What is VDC? VDC is what? It's 12,440. What is my frequency? My frequency is what? It's 60 hertz. What is my capacitance value? It's 4,700 microfarad, which means the only thing which is missing is what? It is your R. Remember, your rectifier already you have determined, which is 12,742 volts, which means here the only thing which is missing, it is for you to find what is R. How do I find R? Which means now I must go and manipulate the formula. Are we together? For me to find R, which means I must go and manipulate the formula. When I manipulate the formula, you know how to manipulate the formula, right? When you manipulate the formula, it's going to be what? Manipulate the formula quickly and tell me what is your R. Manipulate the formula and tell me what is your R. Manipulate the formula and tell me what is your R.
$8.6.
Eh? What?
8
37,404.
You say it's what? 37.
37,404.
37, comma
404.
404 ohms. That is what you got.
Yes, that is what I got.
All of you, is that what you are getting?
Yes, sir.
Okay. Then
Yes,
from
sir.
there, we know that this is the calculated value. But now, because this is the practical circuit, now we need to make sure that we take this value and then we convert it to what? We convert it to E12 series. Remember, I told you that from chapter 2, everything we converted to E12 series. Now, in E12 series, what is going to be this one? It's going to be what? What will be E12 series of this? Oh,
39 ohms.
39.
eh?
39 ohms.
39 ohms.
It's going to be 39
39.
39.
ohms, which means you're going to get a 39 ohm resistor and then you connect it there. Anything
Can I please ask,
yeah.
with those who manage to manipulate the formula, can you please show us how did they do it? Because I did it, but I feel like I did everything wrong. Because my first step was to divide both sides by the VP rectifier.
Which is
After that,
okay.
yes.
You
After
transpose
that,
the one.
yes.
Then it becomes 1 minus VDC
Yes.
divided by VP rectifier. Then, sorry, VDC, you're going to say V, this one, you take this one to this side, which means it's VDC divided by VP rectifier, right?
Yes.
If you transpose this one to this side, and
Yes.
it's going to be what? It's going to be VDC divided by VP rectifier minus 1.
Oh, okay, yeah. I see where I made my mistake.
Then already here it's minus, which means for you divide both sides by minus, which means now it becomes what? 1 minus. You understand? Yes. So, or you saw where you made a mistake.
Yes, thank you.
That is math 1.
Is she?
Did we pass math 1 here? We passed in math 1.
Yes, we did.
But you can manipulate the formula. Okay. Now you have got your 39 ohm resistor. That is the one that you have connected there. Any questions with regard to this?
Sir, can I ask?
Yeah.
So if you're given a resistor and then you're asked to calculate the capacitor and you're given it as it is now, like do I have to convert it into E12 series resistor?
Huh?
If I'm given this resistor 3.7.4, the one that you before converting it, the one that you wrote there, do I have to convert it to E12 series if I'm given it and asked to calculate the capacitor?
No. You will use what is given here because already the circuit, when it's built, it was built according to that resistor, right?
Oh, thank you.
Then the capacitor, you will have to write the capacitor how you find it. Do you understand what I'm saying?
Yeah, I understand.
Okay, sharp. The only time we convert the E12, that is when we are calculating the value of the resistance in our circuit, whereby with this, you will see that the circuit resistance was 37,404 ohms. But now, we need to connect it here. Then we have to go and check. Oh, on the E12, what is that resistor value, which means it's 39 ohms. Then I'm going to get a 39, because the 39 ohm resistor is the one that you're going to buy. Are we together? Because that is an actual resistor. Does it make sense?
Yes.
Good.
Yes.
Then from there, then it says you must calculate the peak ripple. You must calculate the peak ripple factor of the output. How do you calculate the peak ripple? Oh, now I know what is the R. I know what is the equation. What is the equation? The peak ripple factor is given by what? Ripple factor is given by VR. Then it's what? It is your V peak. Oh, sorry, V ripple peak to peak. Let me do this. V ripple peak to peak divided by your VDC. Do I know VDC? Yes, that is VDC, which means the only thing which is missing is what? It is my ripple peak to peak. Oh, which means I must go and calculate that one. How do I calculate that one? V ripple peak to peak will be given by what? It will be given by 1 divided by 2 times the frequency times the capacitance times the resistance. All of these multiplied by V peak rectifier. Are we together? I know what is this is a constant. I know what is the frequency. It's 60 hertz. I know what is the capacitance value. It is what? 4,700 microfarad. I know what is the resistance. What is the resistance? The resistance that I'm using is what? Is 39 ohm resist. Are we together? Then from there, multiply by V peak rectifier. V peak rectifier, oh, it is that one there. Then I will go and say, what is my V ripple peak to peak? What will be your V ripple peak to peak? You don't use this one. You don't use this one. This one is the calculated one, which means this one lead us to get what will be the actual resistor, which is your true resistor, which is this one, which means now this one is the resistance value that we are using. Therefore, now we have substituted into our equation, so into our circuit, our R, it is this one here, which means when we substitute here, we substitute with that value there, which will give you what?
What I
Sir,
got here, it is 579,287.
What?
579,287 millivolts.
5, 7,
9.
9,
Yes.
comma,
287 millivolts.
comma,
287.
it's 579, comma, 57.
287
287
millivolts.
millivolts, which means that is your V peak, V ripple peak to peak. Then from there, now I know my V ripple peak to peak. The VDC already, it is given there, which means now I can go and say, what will be my ripple factor? What will be your ripple factor? V ripple peak to peak, it is this one. VDC, it is this one here. Then what will be your ripple factor?
Sir, before you continue, can you please explain something for me? On
Yes.
the question paper, the formula that they gave us doesn't have 2. How do you come out with that 2?
Were you attending? Did you attend? Have you ever attended the class?
Yes.
Be honest. Be honest. Have you ever attended the class?
Sometimes. Then.
Sometimes. The sometimes it's a problem. The sometimes it's a problem. I told you, listen to me. Listen to me. I told you that the equations which are given in the book, because here you are working with a pulsating DC using both of the signals, which means with the filter, I go and double the filter. Do we understand each other? You go and double the filter, which simply means that these equations here, this is how you use them onto a bridge rectifier. This is how you use them onto a bridge rectifier. Because you're... I'm talking, you're talking.
Ivy, I'm making noise.
Now, your equations, this is how you must write your equations. Even on that textbook of yours, there is an example of this bridge rectifier. You will see that on that example, they showed you that when you do with the bridge rectifier, your filter needs to be doubled. Are we together? Your filter needs to be doubled because remember, you're taking two signals. You're taking positive signal and the negative signal, and then you're pulsating them, both of them, on the first quadrant. Are we together? Which simply means that now your frequency needs to double. That's why you go and say 1 divided by 2 times the frequency. There is your 2 times the frequency. There is your 2 times the frequency. There is your 2 times the frequency. This is the filter frequency because of the capacitor. I hope you understand.
Yes, sir.
Good. Did I answer your question, ma'am?
Yes, I do understand, sir.
Okay, good. You must attend because you will get lost. Then what is your ripple voltage? So what is your ripple factor? Not voltage. What is your ripple factor here?
4,657%. 4,657%.
0.047.
0.047. Okay. And then the other one you said is what?
It's 4,657%.
657%. That is your ripple factor. It's either you write it in this way or you write it in percentage. It still give me the same factor that I'm looking for. Okay. Any question up to so far? Then from there, when you go down, then you must sketch a fully labeled output waveform measured across VO. What is VO? Then if you go up here, oh, this is VO, which means that is your output. Are we together? Your VO, that is your output. Therefore, when you sketch this, now you're going to say, oh, for me to sketch this, this is easy. Oh, now we have got space. Then from there, I'm going to draw my horizons, which is horizontal and vertical horizon. Then from there, remember, your graph always starts from 0, which means starts there, then it reaches the maximum. Once it reaches it was supposed to do pulsating, but now because of the capacitor, which means it will filter. When it filters, then it will do this, which means at the output, that is what you are going to find. But you are going to draw a nice graph, not like mine. Please draw a nice graph. If you draw mine, I'm going to make it wrong. Then you have got your peak, which is your V peak rectifier. You have got from here to here, which is your V ripple peak to peak. Then here, somewhere here, you have got your VDC, which is your VDC. That is your graph. But this, remember, please don't cheat the system, or don't try to cheat the system. This will only exist when the value is correct. Don't just go and draw this with the incorrect values and you think I'll give you marks. No, I will never do that. The values, it must be fully labeled which means when I see this value, when I see this reference, which is VR peak to peak, which means this one also is correct. When I see this one, the VDC, which means the VDC also here, it is correct. When I see the rectifier, which means the rectifier there, it is correct. Please, let's not cheat the system. Any question on those two examples that I did of your filter? Must we move forward?
Yes.
Yes,
Yes,
sir.
Yeah. Then we
Yes,
come
sir.
to when we find a circuit of this nature. This must not be a nightmare. This is not a nightmare. This is a joyride. This is a joyride. It's a joyride. Now, these circuits, they are easy, simple, and straightforward. We have done this. We went this. We looked at this. Now, let's see. It says you must sketch a labeled output voltage waveform. You must sketch a labeled output voltage waveform where where's my cursor? Okay, there. Where of the diode circuit, of the diode circuit in figure 4. This is the diode circuit in figure 4. Now, when you see this circuit, what do you think of? When you see this circuit, what do you think of? When you just see the circuit, what do you think of? Which circuit is this?
Negative clipper circuit.
That is your clipper circuit. Anil, it's a clipper circuit. Are we together? Now, if this is a clipper circuit, now you must be very careful. How are you clipping this circuit? Now, like you said it's a negative clipper circuit with what? With
a negative bias.
Negative bias. Thank you very much. It's a negative clipper circuit with negative bias because you looked at how this bias voltage, it is connected with your diode. Can you see how it's connected with your diode? Which means automatically when you see it like that, then you know that the positive cycle, it is not switching on the diode. Are we together? The positive cycle, it is not switching on but the negative cycle is the one which is switching on the diode. Because the negative side is switching on the diode, then when you look at how this bias is connected, which means it's negative there, then that is your negative clipper circuit with negative bias. Therefore, now you go and check. When I do this, I need to check. During positive cycle, what's going to happen during positive cycle? The diode is going to switch off. Are we together? During the positive cycle, the diode will switch off. When the diode switches off, which means your current, it's moving like this. But this is happening what? During the positive cycle. Are we together? During the positive cycle, the diode, it is going to switch off. When the diode switches off, you have got this one and that one, which are series to each other. Therefore, now because they are series to each other, then your V of R load. Because remember, the only way to get this, that is when you are measuring across your load resistor. Now, your V of R load will be given by what? Will be given by your R load divided by your R1 plus your R load. All of these multiplied by V of supply. Now, V of supply is given in this nature. What is this? What is this? What is this? What is this? When you see this, what do you think of? This one, I'm talking about this one. When you see this, what do you think of? I explained this in class. When you see this, what is this? In what form is my input given?
Voltage peak to peak.
Eh?
Voltage peak to peak.
It's not voltage peak to peak. What is this?
It's V peak.
Thank you. It is V peak. Then here, voltage peak to peak, which means it was going to say from here up to here, it is 400. Are we together? If I say from this peak to that peak, it is 400. That is V peak to peak. But because already it says peak is 200, peak is minus 200, which means this voltage, the way it's given, is a peak voltage. Therefore, already there's no need for me to do any conversion. Already this is in peak. Therefore, now I'm going to say, oh, what is my RL? Oh, RL, it is 680 divided by 680 plus 100, then multiply by 200. Are we together? Which is what? Remember, it's 200 positive because this is happening during the positive cycle. Do not forget, it's happening during the positive cycle, which will give you what?
174,359.
174,359 volts. That is the peak voltage. Now, therefore, this simply means that during the positive cycle, remember, you have got two cycles which are being pushed into your circuit. During the positive cycle, which means you're going to have this signal of yours, then there. Now, during the positive cycle, your positive here is going to be 174,359. This is during the positive cycle. Now the positive cycle completes. When the positive cycle completes, which means now we are looking at the negative cycle, which means we are looking at current in that direction there. Now, when we are looking at current in that direction, you will see that the negative cycle, what is it going to do? It is going to force this diode to go into what? Into forward bias. Are we together? But when it goes into forward bias, it is going to be what? Forward bias, which is happening during the negative cycle. It is germanium. If it is germanium, it simply means that when this diode switches on, it is going to switch on during the negative cycle. During the negative cycle, when the diode switches on, it is going to be what? It is going to be minus 0,3 volts. Are we together? Eh?
Yes. Yes, sir.
People, somebody must just say amen so that I can move forward. Because if you don't say amen, then it looks like whatever that I'm saying, you have got no idea. Okay, minus 0,3 volts. Now, because we know it's minus 3,3 volts, then, oh, I've got V bias. If this is like this, which means my V out, remember, which is my V out in this case, it is going to be my minus VD minus V bias. You still remember the formula that I wrote on the other side of the board when we were in class of the bias. What is your VD? Minus 0,3 volts minus this, your bias, minus 50 volts, which will be what? Which will be minus 50,3 volts, which means your signal is going to be cut at what? Minus 50,3 volts. Therefore, which means that signal, when it gets to minus 50, that is where it will stop. Then it will complete that side where the output already, it is at minus 50, something. Then it comes back there. Then you have got this. Then you will see that now here you have got minus 50,3 volts. Are we together? That is your clipper circuit. Can you see how easy it is?
Yes.
Eh?
Amen.
Yes.
Okay,
Amen.
good.
Sometimes.
Come test.
Sometimes.
The things that you write is going that direction. It's funny how we do all these things. It's funny how we have this class, we do all these things, but at the end of the day, you always do the opposite. But well, that is how it is. Okay, then we come to the next circuit. The next circuit is what? It is a diode clamper. There it was given. A diode clamper is given in figure 5, and it is used for a particular purpose. Draw an output voltage waveform if the diode it is silicon. Remember, you are given what will be the diode of yours. Here the diode, oh, it's silicon. What does it mean? It means that the voltage drop there is 0,7 volts. Are we together? Now, here, which means this one is given as what?
VP.
Already, this is your VP. Now, what happens during this clamper circuit? Oh, what differs from the this one here, which is your limiter, is that series here, you will see that it is what? It is a resistor. Can you see? Series to the supply is a resistor. Series to the supply is a capacitor, which means this is a limiter, this is a clamper. Always check that. If you want to cram, oh, this one is a resistor, which means it's a limiter. This one, it is a capacitor, which means it's a clamper. Oh, okay, which means now I know. But with clamper, we have got two clampers. We have got positive clamper, we have got negative clamper. Here, what am I clamping? Oh, okay. What is forcing the diode to switch on? Which cycle is forcing the diode to switch on? If it is positive, oh God, that direction, high man. This is the negative side of the capacitor. And it says positive must be connected to positive. Are we together? Positive must be connected to positive. But this is positive, that is negative, which means this thing is not turning positively. Can you see?
Yes, sir.
Can you see what is happening? Which means now, oh, the positive cycle is not doing anything. Oh, the negative cycle, it is the one which is switching on the diode at the same time it is charging the capacitor. Therefore, the first thing that you see here, then you will say because of the negative cycle, which means the diode, it is what? It is at forward bias. Are we together? If the diode is at forward bias, then it will have a barrier potential of minus 0.7 volts. Yebo.
You said, why is the diode on the forward?
What is the question?
So the diode is going to the forward bias, right?
Yes.
Good for why ends on Jack?
Go back to your notes. Do you have a note in front of you?
Okay, sir, thank you.
Did you see it on your notes?
I'm still trying to check.
Yeah. So which means you guys haven't studied anything yet.
We did study, sir.
Because the purpose here was for you to do revision. Now, listen. I'm not going to repeat in full, but I'll just highlight. Remember, you have got two cycles, positive cycle and you have got negative cycle. Positive cycle, it will move that direction. That is positive cycle. Are we together? Do you understand that part? Negative cycle will move this direction. That is negative cycle. Do you understand what is happening here? Now, let's see. Which means if negative cycle is moving, which means I've got more positive moving this direction here on the negative cycle, more positive, which means it's positive here, positive there. Now it forces this component to go into forward bias. But which signal is forcing this to go into forward bias? This is the signal which is forcing to go into forward bias. That's why it says minus 0.7 volt. Do you understand that?
Yes, sir.
Again, whoever, if you know you stay in a residence whereby they make noise, please just switch off your mic. Thank you. Now, because the negative cycle is the one that forces this to go into forward bias. Oh, okay, which means the diode will go into forward bias during the negative cycle. That's why I said negative cycle forces the diode to go into forward bias. Okay, sharp. If this thing was connected the upside down, which means positive cycle was going to force this diode to go into forward bias, which means your output was going to be plus 0.7 volt. Oh, because it's minus 0.7 volts. That is the first thing. Remember, the first thing that needs to happen, you need to switch on the diode. When you switch on the diode, also the capacitor must be. These two must have a relationship. Initial relationship. Initial relationship is when this one switches on, that one is charging. You cannot opposite these two. You cannot switch on this and then you are not charging that. It cannot work that way. When you are switching on this one, you are charging this. When you are charging this one must be switching on. That's why I said they must have a relationship. These two must have a relationship. Now, because I am switching on this one, at the same time, I am charging the capacitor. Now, because I am charging the capacitor and I'm switching on this, during forward bias, okay, that one there, 0.7, and then I've got my minus 0.7 volts. Therefore, what does it mean? It simply means that I have initiated graphically the first portion of my graph. What is that first portion? Which means this is your initial turning point. But now, because it is minus 0.7 volts, which means it is going to be your minimum turning point. Sorry, let me take this. It is going to be your minimum turning point. Therefore, here you're going to have minus 0.7 volts. Therefore, which means this graph is going to start somewhere on the positive side and then goes down and then turns there and then comes back there. You still remember?
Yes, sir.
Good. Then from there, what is this point of reference? This is where the graph is starting, because remember the graph now is no longer at 0. It has shifted. Because of this, has shifted this graph upwards up until the turning point, which means up until this turning point here. It's no longer at minus 15 volts, but it is turning where? At minus 0.7 volts. Oh, there, minus 0.7 volts, which means it has been shifted upwards. Okay, I shifted this one upward. What is this one here? What is this one here? Now you will see that, this one will exist when now this component here has stored charge, which means when I find what is VC there. And what is your VC? You know that according to Kirchhoff, it says your V of supply must be equals to what? Your V of capacitor plus my V of the diode. You still remember this equation? This is according to Kirchhoff. You still remember this Kirchhoff?
Yes, sir.
Yes, sir.
Then
Yes, sir.
from there, okay. Now from the, I need VC, which means if I need VC, I am going to say what? Okay. Now my VC will be my V of supply minus my VD. If I subtract this from here, I'm going to get that one there. Are we together? Okay. Yes. Now if I want to do this, what is this one here? This one is what? It is your V supply. It is your V supply during when? During the
negative cycle.
Negative cycle, which means it's going to be minus 15 volts. Are we together? Then minus, what is your VD? Your VD already it's minus 0.7 volts. Are we together? Then it's going to be minus into minus VD, which will be what? Which will be your positive VD, which is 0.7 volts. Therefore, here you're going to have 14.3 volts. But what? Minus 14.3 volts. Because you are charging the capacitor with the negative cycle, which means you will charge it by minus 14.3 volts. Are we together up to so far? Do you understand?
Yes, sir.
Because
Amen.
because the graph was shifted upwards, the voltage that you determined here, it becomes your reference voltage. But now this reference voltage, now because of the location, how the graph has been shifted, which means this value, now we find it on the positive side, which means it becomes 14.3 volts. Do you understand this part?
No.
What is it that you don't understand? What is it that you don't understand?
I got it, sir. Thank you.
Okay. Then from there, oh, okay, this is my point of reference. Remember, from here to here, nothing changed. What is the amplitude? From here to here, what is the amplitude?
15.
Amplitude is remain 15 volts. Are we together? Amplitude will remain 15 volts, isn't it?
Ask.
Remember, this circuit doesn't change the amplitude. It doesn't temper it only changes the location of your signal. Therefore, when this signal turns positively, on the positive side, which means from here to here, it is what? It's 15 volts. Are we together?
Amen.
Therefore,
Yes.
now it simply means that from here to here, if it is 15, therefore, location is 14,3. It's going to be this one plus that one. Now it becomes what? It becomes 29,3 volts. Anyone who's lost?
Sir,
Yeah.
can you please repeat the reference where you said negative 14,3?
Yeah?
Can you please repeat the reference? Because it's negative 14,3, but we wrote it as positive.
Listen. This, the initial, this point here. Can you see this point here? Can you see this one here? Your negative cycle. Can you see this thing? The first thing that you did. This one will show you how are you pushing your cycle. How are you pushing your input? Are you pushing your input upwards or downwards? Do you understand what is happening here?
Yes.
Because it's of a negative cycle, it simply means that the first turning point is going to be minus 0,7 volts. If this is 15 here, minus 15 here, where is minus 0,7 volts? Is it minus 0,7 from 0 to 15 or it's from 0 to minus 15?
0 to minus 15.
What does it mean? It was turning on what? On minus 15. Can you see?
Yes.
Because of this diode, which says now you need to turn at minus 0,7 volts. What is going to happen to this signal?
Shift up.
Which means you're going to shift up. When you shift up, you will see that now this 0, it is left there without anything. Then you're going to shift your signal up until this turning point here,
Which is negative.
lies within what? Minus 0,7 volts.
Yes.
Because it lies at minus 0,7. Remember, from here up to here, it's still 15.
Yes.
Do you understand?
Yes.
So if from here to here, it's still 15, what does it mean? It simply means that because of the 0,7 where this thing is, it's sitting, then this 0,7, when I subtract it from 15, what do I get?
14,3.
This is your 14,3.
Yes. Okay. Thank you, sir.
Any question? Now, that is your positive clamper circuit. Then you swap this thing around, then you do your your negative clamper circuit. Okay. That is the first one. On the clamper. Then, the next one we're seeing what? The Zener diode, which is chapter 3. which means we summarize there, we summarize everything, rectifier, clipper, and clamper. Then we come to chapter 3, which is Zener diode. Oh, Zener diode. Now here it says, consider the following. So consider the circuit diagram of Zener in figure 6. All calculations must be shown. Then from there, I'm given the figure. It says power supply, transformer, rectifier, filter, which means it lies there. Then from there, the output here that you get is what? It is your VDC. Can you see? It indicates that there you are measuring VDC, which means at that point you are measuring VDC. VDC, it's supplied into a regulator. This is your regulator circuit. Oh, regulator, I find Zener connected in this way. In parallel with this, I find my resistor. Oh, I'm familiar with this one. VDC, I don't know what it is, but I'm given this one here. I'm told it's a regulator, which means this circuit is regulating here. Now, here it says, what is the question? 5.1, it says calculate the minimum input voltage that can be used to regulate this specified Zener diode. What is the specified? Oh, that is the specified Zener diode. What do I need? Minimum input, which means I must find what is the minimum input voltage. And for me to find the minimum input voltage, which means that is when the Zener it is at its lowest point. When Zener it is at its lowest point, what does it mean? It simply means that at IZK, that is when Zener it is at its minimum operational point. Therefore, now I am given the Zener part number. If I am given the Zener part number, oh, I need to find the Zener part number. Then I'll go and say, oh, somewhere, let's see, not here. There. Somewhere here, I've got what? I've got my Zener data sheet. It says it must be 444. Oh, 444 is this one here. Can you see the 444? I need to find, oh, I've got this one, which is my V of Z. Oh, okay. My test current, which is that one there, 17. My ZZ, which is 14. Then my IZK, which is 0.25. Oh, there my power dissipation of Zener, which is 1 watt. Those are the parameters that I need in order for me to be able to complete the working of this one here. Now, you have done the catching up of those one there, then you go to your circuit. Oh, in my circuit, what do I need? I need my V of Z. What is my V of Z? Oh, V of Z says it's 15 volts. I need my IZT. My IZT, it says it's what? 17 milliamps. I hope I'm writing the correct thing. Then I need my ZZ. My ZZ, it says it's 14 ohms. I hope I'm writing the correct thing. Let's see.
Yes, sir.
Yes, they are correct.
Okay. Now, oh, my ZZ is that one there. Oh, what is my IZK? Okay. Oh, my IZK is 0.25 milliamps. Okay, I have got this data sheet. Now, with this data sheet, how do I work with this IZK? At IZK, the first thing that I need to do when I work with Zener, I need to find what is V out. What will be my output voltage at this minimum? My output voltage at this minimum, which means it's going to be your V of Z minus your change in V of Z. Okay, what is this change in V of Z? Oh, change in V of Z, it must be my IZT minus my IZK, all of these multiplied by my ZZ. Are we together? Now I know what is IZT. Okay, IZT. I know what is IZK. IZK. I know what is ZZ. ZZ, which means I can be able to find what is my change. So what is my change in V of Z? Then I take the change in V of Z, then I subtract with the V of Z. What is the V of Z? Oh, it's 15, which means it's going to be 15 minus, in brackets, 17 milliamps minus 0.25 milliamps multiplied by my ZZ, which is 14. Up to so far, are you having a problem with this equation here? So far, are you having a problem with this equation here?
No, sir.
Good. Now, once you find your V out, now you substitute, you find the V out. Once you find your V out, okay, they want the minimum input. How do I find the minimum input? Remember, I'm going bare minimum. I'm going to the lowest. How do I get to the lowest? Okay, V input, but I need it at the minimum. V input at the minimum, it will be given by V out at IZK. Then plus, because I am at the bare minimum, which means I am at IZK, which means it's going to be IZK multiplied by, already here, I know what is the voltage, which means it's the voltage that I see there. Then there is this load resistor connected there. Remember, this voltage plus this voltage that you find here must be equal to the supply voltage. That is Ohm's law. I know that one there. Okay, if I add this one, oh, I must add with that regulator resistor, R limiter that I see there. Then I must multiply this by 180 ohms. Then I will know what will be my minimum input voltage. Are you having a problem with this equation here?
Sir, can you please repeat the one that you just wrote right now?
Which one?
V in minimum. VP minimum.
V in minimum.
Yes.
Minimum.
Yeah, V in minimum. And if you found your V out at IZK.
Yes.
Minimum simply means that in the beginning, remember, if you look at your Zener characteristic curve, you have got this part. Then you have got this one here. The minimum is at the knee. That is when you are starting to regulate, which means here, that is where you find your IZK. Do you understand that?
Yes, sir.
Now, with the IZK, this is your current, that is your voltage, which means because it's a knee, it's a curve, then you have got your change. Your change in V of Z, you find it here because it is what? It is the, what do you call this? It is a curve. Therefore, this is where now you will find a point within this magnitude here. That point that you find within this magnitude here, that is your V out at IZK. V out at IZK must go with IZK. Do you understand what I'm saying?
Yes, sir.
Then somewhere here, that is where your IZM is. So which means the voltage that you find here, it is V out at IZM. Which means V out at IZM must go with IZ. Remember, for this component to work, it must work within this magnitude here. Can you see this portion here? That is where this is the functioning of Zener here. You regulate your Zener here. In the middle somewhere here, that is where you regulate your Zener. Because there is a point here, which is your IZT, which is the test current. It's like a reference current. Reference from the middle to the lowest, from the middle to the highest. Do you understand?
Yes, I understand.
Yes. So now for us to find the minimum, what is the minimum value that we must put into our circuit so that the Zener can start regulating? That's why here it says, calculate the minimum input voltage VDC, which is this one, that can be used to regulate the specified Zener diode. This is the specified, which means at its minimum, what must be the value of VDC so that this Zener can start regulating? Oh, okay. How do I get that? I need to go to minimum. When I get to minimum, it must be IZK. What happens in IZK? V out is equals to VZ minus change in VZ. Minus change in VZ because I'm at minimum. Always, it is from the test point to the minimum. Are we together? Multiply by ZZ. Therefore, for the input, it must be, now, if I add the voltage that I measure here, this voltage, if I measure this voltage and the voltage that I find here, remember, what Zener gives, it is what is going to appear there on the load, which means this voltage plus that voltage must give me the supply voltage. Do you understand that part?
Yes, I understand.
But now Zener works in two ways. It works in minimum and it works in maximum so that we can determine the regulation point. Remember, your regulation point, lies within where your test current is. That is where it lies, your Zener operational point. It cannot start operating before it reaches the minimum. It cannot operate if it goes above the minimum, which means it must work within the minimum and the maximum. Therefore, now I need to check during minimum, what's going to happen with Zener? Oh, it's starting to regulate, which means it's starting to give me 15 volts. Then from there, what must be this input voltage? Oh, the input voltage must be this voltage plus that voltage. What is this voltage? This voltage, it is when it on its minimum. Here, what is happening? Oh, on this one, which means the minimum current that the Zener is starting to regulate, which means that will be the minimum current there. Therefore, for me to get that, it must be the V out at IZK, which is this one, plus IZK minimum operational current multiplied by what is the value there. Remember, this is Ohm's law. Here, this is Ohm's law, basic Ohm's law. Are we together?
Yes.
Yes,
Amen.
sir.
Good. Then from there, now because we have determined this, okay, now we know what is our V in minimum. Then the next one, it says it needs to calculate what is the maximum input voltage that can be used to regulate Zener. That can be used to regulate Zener. What happens? Okay, now maximum, okay. What happens in maximum? It simply means that now it's looking at that point there. Can you see? My class ends at 8. Can I call you after 8? Now I'm at what? Now I'm at IZM. Okay, this is my IZM, which means the maximum that this thing can push up to. Then I have to go and say at IZM. What is happening at IZM? Therefore, at IZM, now I need to go and check. It must be V out is equals to, now it must be your V of Z plus your change in V of Z. What differs is, at maximum we add, at minimum we subtract. Are we together? At maximum we add, at minimum we subtract. But your change, it must be what? It must be your IZM, which is the maximum operational point, minus your IZT, as I've already explained. Remember, it must be from the maximum to the minimum, so to the middle, then multiplied by, this one is going to be your ZZ. Okay, what differs between these two? It's from the test point to minimum. It's from the maximum to the test point. Can you see what is happening here between the two?
Yes, sir.
Then from there, oh, okay, now I know this. Once I find this one, what does it? Oh, it wants the maximum input, which means for the maximum input, I need to do what? I need to go and say V input. But it's happening when? It is happening during the maximum. What is this maximum? It is going to be my V out at IZM. I have calculated V out. This is V out at IZM. Then plus, because I'm working with Ohm's law. Okay, what is the current? The current is the maximum, which is your IZM. It must be IZM multiplied by the resistor, which is in series with the input, which is what? Which is 180. Therefore, I will find what is the maximum output voltage. But now, here you will see, oh, it's talking about IZM. If I look at this thing here of mine, if I look here, okay, I've got this V, Z, IZT, IZK. Oh, okay, what is missing? Oh, IZM. How do I find IZM? Then for me to find IZM, I know that IZM will be given by power dissipation divided by V of Z. That is my IZM. Do you understand what is happening?
Yes, sir.
Yes.
Yes, sir.
Then you have managed to solve those two problems. Any question?
Sir, it's
Yeah, Bo.
on the change of VZ, it's IZM minus IZT, right?
On that?
On the change in VZ.
We change in VZ.
There on V out, like on the formula.
Which V out? Remember, we've got two V out.
Okay, the first V out, like the on 5.2.
5.2 is this one, the maximum. Mm-hmm.
Yes. So IZM is the maximum, right?
Yes.
And then IZT is still the same IZT we used previously.
Remember, did you understood this graph? Did you understood this graph?
Yes.
What did I say is happening here? This is the minimum when it starts. This is the maximum when it stops. Do you understand that? This minimum and maximum, they must have a point of reference. What is that point of reference?
IZT.
IZT. Does IZT changes?
No.
No. This one will give you the limit upwards. This one will give you the limit downwards, which means your operation works within this point here, which is your IZT. Your IZT moves down, upwards and downwards, which means it's either it's going to work from here up to there or it's going to work from here up to there. But it cannot go beyond IZM, and it cannot go less than IZK. I would get. But even though it cannot go less than this, above this one here always gives us a point of reference. Do you understand that? Eh?
Amen.
Good. Any question?
Yes, sir.
Now.
Sir.
Yeah.
So if we are required to calculate to find the maximum value of RL, let's say they didn't give us RL or the R limiter, and how are we supposed to go? How are we supposed to calculate that one?
How are you supposed to?
Calculate the maximum value of RL if it's not given. Let's say they will give us the V in, and then they give us they will just give us V in, and then they ask us to calculate the value, the maximum value of RL.
Do you have a note in front of you? Eh?
Yes, sir.
Are you sure you have your note in front of you?
I have, but
Okay.
the problem is I don't understand the part whereby we have to calculate the value of R limiter.
You don't understand the part where, okay. Now,
Yes.
here, can you see where we are? here.
Yes, sir.
Can you see this one here?
Yes, sir.
Can you see this one here? This is the equation of calculating the R limiter. This one. You are talking about this resistor, Anel?
Yes, sir.
This is the equation. For you to calculate the limiter, with the limiter, we need the maximum value that we can use so that even the current, it comes in any direction. This resistor will be able to limit that current when it is high, which means we must go all the way maximum. Do you understand what I'm saying?
Yes, sir.
Which means for us to do that, then we're going to say our R limiter will be given by our V in, which is the specified V in, and minus,
Yes,
then it must be V out. V out, it is happening when? It is happening when our output, it is at its maximum. Are we together? Are you following this?
Yes, sir. I now understand, sir. Thank you. I understand.
Divide by
Thank you.
your IZM.
Yes, sir. Thank you.
Any question?
Sir,
Yebo.
will they give us the formula sheet?
But yeah. We're working, you see, we're working without even formulas here.
But say,
What do we need formulas for?
We
At
least, sir, for the first part, the one year bridge rectifier, please. That one. At least this one we will be able to.
Yes.
Which part?
The bridge rectifier.
I think if the formula comes, they might, I'm not sure. People, please don't get me wrong. I am not sure. But they might come looking something like this.
Yeah, that's all we need.
Yeah.
Thank you.
Let me see. Is it a full one? No, this is not a full one. When did I see this? I saw it somewhere. I can't remember. But can you see? Okay, for example, can you see this one here? Can you see this one here? Can you see how it's written?
Yes, sir. Yes, sir.
This is from the book. Can you see? What is missing?
The 2 in the frequency.
Thank you.
Yeah, the 2 in the frequency.
This is what you are going to do. This is what you are going to do. You are going to rewrite this formula as it is. And then you calculate, and then you must. But sir, this is how you gave it to me. I am telling you now. If I give it to you like this, now remember that what is going to happen is, if you do something wrong, you're gonna get it. So you're gonna get it wrong. Are we together?
Yes, sir.
So avoid. Can you see your change in V of Z? Eh? Can you see your change in V of Z?
Yes, sir.
Yeah? This is your change in V. That's why I will hint you. I cannot give you full. I will hint you. Yeah?
So I feel like at this point, it's just a matter of us remembering the formulas, because this hour.
It's a matter of you going. It's a matter of you going to study, not going to cram the formulas.
Then we have to. Oh, okay.
Yes.
You have to go and study.
Yes.
Because if you go and cram the formulas, you will have a problem.
It's not cramming, it's remembering.
Yeah.
Yeah.
Only around that time.
The more you practice, guys, can you see? The more you practice, the easier it becomes. If you leave it for Thursday, you starting to study at Thursday. I've given you 2 weeks already. Last week, we didn't do anything. That was your week for you to go through. Today, this week, it's the week whereby now we are recalling everything that we have done. If you are still sitting on the verge of saying, I'm starting to study this week, now you're going to have a problem. Any question? Okay, this is what I'm going to do. I am going to give you other circuits and other exercises to go through. Now go through them. Then on Wednesday, we're going to have the same session for 2 hours. Then you will ask questions based on those things that I'm going to give you. I'm also going to give you also this one that we're doing now. I'm going to give you 2 things. I'm going to give you this one that we are doing now. We have done this one here.